Hello guys, Saduma here. Today's lesson is a follow-up of lesson 2 where we were discussing relations and some of the issues that we were on yesterday were related to the symbols and notations. What happened though is that we didn't have enough time to look at some of the questions that somebody might want to ask you with regards to relations and functions. And so in this lesson, we're going to look at some of those examples. But first of all, I just want to summarize the discussion, okay? And that a relation is simply an association between two quantities x and y, right? That such a relation can be represented in different forms. So what we are going to do now is summarize very briefly, okay? That given a relation between two quantities x and y, we can represent such a relation using what we call a relation notation, as we will later see that this is also called a function relation under specific conditions, right? So this means that for a relation x, x can be mapped, relation R, x can be mapped onto another rule y, okay? And that the rule y is usually expressed in the form of an equation. And I think I gave an example with the case of a car that consumes 8 liters for every 100 kilometers, all right? The rule was that y was 12.5 multiplied by x, which is to say, if I write this in the form of a relation, there it is, then that means that if I put an amount x liters, I get 12.5x kilometers. So this is what we meant by a relation notation, okay? Just to clarify, so that means if I put 1 liter there, then 1 times 12.5 means I get 12.5 kilometers. If I put 10 liters there, if I put in 10 liters, then 10 times 12.5, I get 125 kilometers, and so on, right? So this is a relation notation. We also talked about the set builder notation, but that is coming up shortly in an example. So we will start with question 1 here. This is to remind you of some of the symbols we've used already at the beginning of MYP5. We know about these symbols for special number sets. Okay, so let's look at a question on this. It says complete the table by placing a tick in the appropriate box if the number is an element of the set, and put a cross otherwise, all right? So if it's not an element of the set, you'll put a cross, okay? In lesson 2, we've discussed this, but I thought that maybe for students who are taking Maths AI and perhaps AASL, that perhaps we look at this a little more closely and put a better presentation, and that hopefully this is going to make it clearer. Okay, so here is a table, we need to fill it. Perhaps the best way is to go column-wise. So we look at a symbol for a set notation, a special set notation, and we see if these numbers fall in that set, okay? So what does n refer to? You can pause the video and think about the set notation n. Okay, the set notation n refers to natural numbers, also referred to sometimes as counting numbers because they are the numbers we use for counting objects, right? 1, 2, 3, 4, and so on. The notation, so by definition, that is the set n. The set n is the set containing elements such as 1, 2, 3, 4, and so on. We refer to these as counting numbers or natural numbers. So looking at this 3 numbers, therefore, which one falls in the natural number set and which ones do not? So if it falls in there, we put a tick. If it doesn't, we put a cross. So clearly 2 is in this list, all right? So 2, under 2 we put a tick. Square root of 3 is about 1.732 and so on. It is a non-terminating, non-recurring decimal, and therefore it is not a natural number. As a matter of fact, we will find out that it is an irrational number. So root 3 gets an x. Similarly, minus 2 over 3 is the same as negative 0.666. That's recurring decimal. A recurring decimal does not fall in the counting number set, and therefore that also gets it wrong. We move on and to the next set. Again, give it a moment and think about what that set refers to. You can pause the video, and assuming you've done so, this is the set of integers. That's the symbol we use for a set of integers. And what are integers? Integers are the numbers on the number line, the whole numbers on the number line, both positive and negative, and including 0. I don't want to just say whole numbers, because whole numbers also has a complete different meaning. It has a symbol here, W, capital. Okay, so I'll use the word whole numbers, but also say positive and negative, including 0. Okay, and so there is the set of whole numbers. This continues that way to infinity and this way to infinity. All right, and so looking at our 3 numbers there, again we can tell that 2 is in the set of integers, but root 3 and minus 2 over 3 do not fall under the set of whole number, positive or negative. Okay, all right. The third one there, Q, think about it. Well, Q comes from the word quotient. So in the same way that a product means multiplying 2 numbers, a quotient means dividing 2 numbers. So A divided by B, all right? So any number that can be expressed as A over B, where A and B are integers, but B cannot be a 0, such a number would be referred to as a quotient or a rational number. So this is the symbol we use to represent rational numbers. Okay, let's just write that down first. Rational numbers, and a rational number can be expressed as A over B, where A and B are any integers. So we pick from the set of integers here, whole numbers, negative and positive, except the value of B, the denominator, cannot be a 0. If it is a 0, then we have an undefined quotient, which we cannot place in a set. Okay, and so looking at our 3 numbers there, which ones qualify, which one can be expressed as fractions of A over B, and clearly 2 can be expressed as A over B, because we can write 2 as 2 over 1. We can write it as 4 over 2, 6 over 3, and so on. And therefore, we can write it as negative 4 over negative 2. Okay, so that makes 2 a rational number. Root 3, once again, cannot be expressed as a rational number because it is a non-terminating decimal. Decimals can be rational numbers. 1.2 is a rational number because I can write this as 12 over 10, and I can write it as 6 over 5. All right, that makes 1.2 a rational number. So being a decimal does not mean it cannot be written as a rational number. But if it's a decimal that is non-terminating, if it is non-terminating, continuing to infinity, then we say it is an irrational number. It cannot be expressed as a ratio. It cannot be expressed as a fraction of 2 quantities, two integers. All right, and therefore root 3 fails as a rational number. What about minus 2 over 3? Well, negative 2 over 3 minus 2 over 3 can be written as minus 2, that's an integer, divided by 3. But we can also write it as 2 divided by negative 3. Either way, they mean the same thing. And so that last one can also be expressed as a ratio of 2 integers. Okay, so because of that, we can conclude that 2 is a rational number, root 3 is not a rational number, and minus 2 over 3 there is a rational number. Okay, we go to the last column. Capital R there refers to numbers that are real. Okay, a real number is any number that can be found on the number line, whether it is negative or it is positive, it is a decimal, it is rational or irrational. All of them, any number that can be found on the number line is a real number. Okay, so this includes numbers, irrational numbers like pi. So the Q with an apostrophe there means irrational number. So if this is rational, then that refers to as irrational numbers. Okay, so what are irrational numbers? Root 3 is one of them. Okay, root 2, root 5, but also some special numbers like pi, 3.14159, and so on. A number like E, the special number E, 2.7. The number E is 2.718, and so on. Pi, okay, 3.1415, and so on. I think there's a 9 there. All these are non-terminating, non-recurring decimals. These are referred to as irrational numbers. The square root of 2. The square root of 2, 1.4142, and so on. The square root of 3, okay, 1.732, and so on. These are irrational numbers, and they all fall under the set of real numbers, including the other numbers that we've talked about. Okay. Right. So, for that reason, all these numbers here are real numbers. Okay, so they all fall under the set of real numbers. So part A of the question is then sorted out. Part B says a relation R is given by, notice that this capital R is different from the set symbol R. Okay, so we are not saying the same thing here. This is a set symbol for the special set of numbers called real numbers. The R we are using here, this R is a relation. Okay, so it's the regular R. So a relation is such that x maps onto 2x squared minus 3x. That is a relation notation right there. And the x is an element of the set containing negative 2, 2, and 3. This is a set builder notation for the domain of this relation. Okay, so the question is, draw a mapping diagram to illustrate this relation. Okay, and part 2 is to write down the range of R. Okay, so draw a mapping. So to do a mapping, we need those two circles or ovals, one for the input, the other one for the output. Okay, so one is for X, the other one is for Y there. Okay, I have put some kind of a machine that we can feed our data into, our input into, to get an output there. Let's see. So the first element in the input is negative 2. So if we put negative 2, here is my machine with the rule on which the machine is operating. So if we put in a 2 in there, okay, put in 2, it's churned in. Effectively what we are doing is we are replacing x with 2 there. So what happens? If we put 2 in place of x, negative 2 in place of x, and put it there, negative 2 squared, that's an even power, so that becomes positive 4. Positive 4 times 2 is 8. Okay, so we have 8 there, and this one is negative 2 times negative 3, which is 6, positive 6. So we have 8 plus 6, and that gives us 14. So we expect that the output here should be 14. Okay, so we get an output of 14 when the input is negative 2. And so we put 14 here and draw the mapping, an arrow to indicate the mapping. Okay, feed in 2, which is the next number there. If we feed in 2, the same thing will occur. So we let 2 go in there. And if we put 2, we can try this also. So we have 2 into 2 squared. Now x is 2, and we say minus 3 into 2. Okay, that gives me 8, but now minus 6. So I expect the result to be a 2. All right, so if we feed in 2 inside there, I expect that the machine will give me a 2 outside, and that 2 is what we feed here and draw the mapping for it. Okay, lastly, we can feed in the 3. So the next number there is 3. If we feed in 3, what happens? Okay, put in 3 and calculate. We have 2 into 3 squared minus 3 into 3. This is 9, 3 squared. 9 times 2 is 18 on this side, and this is minus 9. So we expect the result to be a 9 when we feed this into the machine there. We'll have a name for this machine later. Okay, so we expect a 9 out there, and that 9 is what goes onto outside there, and we draw a mapping for it. And so this is the mapping diagram for the relation R. Okay. All right, so we are done with the first part, drawing a relation, a mapping diagram for that relation. The second part is for us to write down the range of this. The range refers to the values of y. So in set builder notation, so we just have to say y is an element. We are done with the first one. So here we say for the range that y is an element of the set containing 2, 9, and 14. That is the range of this relation. Okay, I hope that is clear. Let's move on. Okay, here is a question. For each of the graphs of the relation, we have several of them coming up. Okay, use the set builder notation to write the domain and the range of the relation. And part B, you are to state whether this relation is discrete or continuous. And part 3, you are to write a relation notation for this mapping. Now I want to do this one because I want to remind you of a few things that you might have done earlier and you probably would forget. So let's see, we did this in lesson 2, but it was a bit fast. I thought that to help students in AI to go a little bit slower and also to organize the working a little bit better, so you can follow. All right. So here is a relation. This kind of a relation is called a piecewise relation because it has got different parts. So this is a part that is different from that, that is different from that. There is a distinct change in the rule determining the value of y for value of x. Okay, so there are 6 different parts, 1, 2, 3, 4, 5, 6. So we refer to this in general as a piecewise function. Another thing I want you to notice is that at the beginning we have a circle that is not filled, and at the end we have a circle there that is filled, and these have meaning. So let me just complete that first. If you are given a line like this, I'm hoping that you did this in an earlier class, but if you didn't, just as well, because we are looking at it now. So just in case you haven't done this before, think of this line here. We want to know the values of x that represent this line. What are the possible values of x along this line? Well, we know that at this end, the value of x is 2 there, and on this end, the value of x is 5. So obviously, x lies between 2 and 5. That's what we would do. Now, the unfilled line there means that although this is the boundary for possible values of x, the unfilled circle means that 2 is not part of this list. So if we were to list all the possible values of x, we would put any number along this line except we cannot put 2. So this means that 2 is excluded. Excuse me. All right. On the other hand, the 5 here means that 5 is part of that domain. So in fact, here this remains like this to say that x has to be greater than 2, but x can also take the value of 5. So this is what this means. Okay. All right. Another way of writing this, I'll come to that shortly, but generally, so that's what that means. So this here also means that if I was looking for the domain for this relation, I can say that the domain lies between -5 and 5, but -5 is not included. -5 itself is not included. -4.9999 to whatever number of decimal places you like is accepted, but -5 itself is not in the domain, okay? On the other hand, because this is filled, the 5 is in the domain, okay? So that's what this means. So let's see what we have then. Let's see what this gives us then. So what's the domain? So we can write the domain as x are any real number such that that real number lies between -5 and 5, but -5 is not included. So x has to be greater than -5. Okay, it's not greater than or equal to -5 now. It is greater than -5, but it is less than or equal to 5 because of that. Okay, so this is how we represent this domain. What about the range? So similarly, the range would be x if this were not here and this only ended, say, up here, we would say that the values of y starts from -2 to +2, and we would say greater than -2 because of that, and less than or equal to +2 here. But we have this which is acceptable. This is -2 is acceptable, and -2 here is also acceptable, all right? So for that reason, we can ignore that and say that the range falls between -2 and +2 inclusive. Okay, so -2 is accepted because of this part here and because of that part. So there is the range of this relation. So y are all real numbers that fall between -2 and 2, both of which are inclusive. Okay? All right. Something else, very briefly. If this was, so like if I have that line there and both sides are filled up like that, and let's say this is A and this is B, all right? So that means this end is acceptable and that end is also included, all right? And these are values of x. So one way to represent this would be to say x lies between A and B inclusive, all right? Another way to represent this, which is a much shorter and more subtle way of expressing this, actually neat, okay, is to put these square brackets like that. So put that and a comma and a B. So this is another way in IB that we represent this, okay? If instead this looked like this, so like the case that we just discussed earlier, this one here, okay, if this is x, which we say x is, this is A and B, so x is greater than A and less than or equal to B. Okay, to represent this using this notation, we would say A, comma B. B is acceptable, so the square bracket faces inwards, but A is not acceptable, so the square bracket faces away from the 2. Okay, so this is another way of representing this. What about if both of them were not acceptable, like that and like that, and this is A and this is B. Then to represent X, this is X is greater than A and X is less than B. This I would represent like this: A, B, the square bracket faces out, and on this side also it faces out. So we can have different arrangements of this depending on what's on this side and on this side. So this is another set, another way of representing this range of possible values of X. Okay? Yeah, I hope this is clear. You don't need to worry about it so much now, but just to know that another way of representing this is this here. Okay, if the square bracket faces out, it means that is not included in the set. That means less than, right, or greater than A, right? If it's facing inwards like that, if both are facing inwards, meaning both are acceptable. If one is facing away or both are facing away like that, that means it's not acceptable. But let's move on. So notations are a way of reducing the writing, okay? A simple way of putting a lot of information on one page, but writing very, very little. So provided we all understand the language, notations make mathematical work very, very easy to read. Symbols and notation. Right, and move on. And so that's the domain and range. So here I could have used the brackets instead of the square brackets as opposed to this. All right, state whether this relation is discrete or continuous. Well, obviously, the relation, just to cut it short, if we have a line, which would mean X has infinite possible values between -5 and 5. There are infinite possible values of X there. That means the relation is continuous. So if we see a line like this, it means a relation is continuous. If a relation is represented on a graph by points, then we know that relation is discrete. Okay? So we'll not waste time here. This relation is a continuous relation. Okay? Going back, sorry. All right, so this is a continuous relation. The domain contains infinite possible values of X, anywhere between here. So I can have 3, I can have 3.5, I can have -3.2, -3.005, -3.142, whatever you like. There are infinite variations within this domain -5 to 5, okay? Now, the part that is important for reminders is to write a relation notation. Now, to write a relation notation, what we want to do is to be able to express this as R is such that X maps onto some Y. Okay, and then we want a rule for that Y. Okay, we want the equation. The problem is that every section of this relation has a completely different rule for determining the value of Y. So it means we have to find those different rules. We have to find the rule for this section. Basically, we are saying we need to know the equation of this line, we need to know the equation of that line, equation of that line, and so on. So once we found the equations of the line, then we will write this relation notation for this relation. Okay? Excuse me. Okay, so let's see. What I have done is to name the different parts of this piecewise function. Okay, so the equation we're going to, because these are all straight lines, we need the equation of a straight line. Okay. If we are going to find the equation of straight line, we need some of the coordinate points. Okay, so I'm just putting in some special coordinates, some coordinate points that I'm going to find useful, that, this here, and maybe this one and that. So if we put, yes, this is the point 0, 2. I probably don't need this or this, but I need that one there. and probably the end there. Okay, so we have those coordinate points, and we have 6 different lines. So we are going to use y is mx plus c for the 6 different lines. That's line 1. We'll call that line 2. Line 3 with a negative gradient. Line 4 is horizontal. Line 5 has a positive gradient. Line 6 has a negative gradient. Okay, so starting with the first one. Okay, the equation of the line is given by y is mx plus c, where m is the gradient of the line and c is the y-intercept. So this line here, if we continued it, it would go and cross the y-axis somewhere up there. What's that value of y? And that is the value of c. Okay, so straight away looking at this, what's the gradient of the line? Well, the gradient of a line m is given by the change in y over the positive change in x. By how much? So if I move from this point to that point, by how much have I increased my value of y? By how much have I risen? Okay, as I move in the positive x direction. So moving from here to there means I move 2 steps in the positive direction there. So we always move in the positive x direction, and therefore to get there I must rise. How many? 4 steps. Sorry, that line is a bit crooked, but from this point to that point is 4 steps, and from this point to this point is 2 steps. So the gradient is the change in y, in this case positive 4 over positive 2, which gives me a 2. So I know the gradient of the line 1 is positive 2. And I will reason like that. What about this one here? What about this one? Has a gradient of 0. What about this one here? Well, as I move from this point to this point, I move 2 steps forward, so that's positive 2. But in the y direction, I move negative steps. So therefore, I have negative 4 steps, according to change in y over change in x, negative 4 steps over positive 2, and that gives me a gradient of negative 2. What about this one here? This is horizontal, so the gradient is 0. What about this one? This one has a positive gradient, because as I move in the positive direction of x, that's 1 step, I rise 2 steps, positive 2 steps in the y direction. So the gradient is 2. And similarly, the gradient of the last line there is negative 2 for the same reason. Okay, so using that, using those ideas, just reminding you how to find the gradient. Well, if you can't remember to do it like this, or if we did not have grid lines. See, here we have grid lines, so we can find the gradient by doing that. But if we didn't have the grid lines, then we can make use of the 2 points that we know. Okay, and use the relation gradient is change y2, we say m is y2 minus y1 over x2 minus x1, and then we would use that to find the gradient. Okay, but right now we don't need to do that. We can find the gradient a little faster using those grid lines that have been put. Right, and so with that in mind, line 1, the gradient is 2, so I can write at least y is 2x plus c. Okay, then I pick one of the 2 points. Let's take that. Okay, when x is negative 3, y is 2, so I can say 2 equals 2 into negative 3 for x plus c, and when we rearrange that, this is negative 6, but when we take it to the other side, it becomes positive, so c is 8. And so the equation of this line, in other words, c is 8 means this line is going to cross the y-axis at a point where y is 8. Okay, so the equation for line 1 then is 2x plus 8. Y is 2x plus 8. Okay, the equation for line 2 is easy. This is a horizontal line, so the gradient is 0. M is 0, so this term disappears. All we are interested is in the y-intercept, and this graph crosses at y is 2. So the equation of line 2 is simply line y is 2. Okay? Excuse me. So the second line has the equation y is 2. The equation of a horizontal line is really straightforward if you think about this formula. Okay, line 3, the gradient for line 3 is negative 2, as we had said, right? So again, negative 2, 2 times negative 2 into, because m is negative 2, so we can write y is negative 2x. Okay, y is minus 2x plus c, and then we pick a point, that very point there, and we say when x is 0, y is 2, so 2 equals, this is 0 there, so minus 2 into 0, this disappears, plus c, so obviously the y-intercept is c is 2, and so our equation is y is minus 2x plus 2. That's the equation of line 3. Okay. So we use the very same approach to find the equations of each of the lines. Try them out with the other lines. We can see line 3 has the equation y is minus 2x plus 2. Line 4 is horizontal, just like that one, so we just need to know where the line would cross the y-axis, and that's negative 2. And we say line 4 has the equation y is negative 2. If we look for the equation of line 5, using the same methods we use for line 1 and line 3, you should try it out. You should be able to see that the equation is, for this one, the gradient is positive, so 2x minus 8, meaning this line, if we extended it backwards, it would cross the y-axis at y is negative 8, okay? And this one, if we extend, this has a gradient of negative 2, so we would write negative 2 something, okay? And it will go and cross the y-axis up there. Check it out on your own, and you should see that you come up with the equation y is minus 2x plus 8. Okay, so now we have the equation of all the 6 different pieces of this relation. Okay, I have summarized them here. So now then, how do we write the relation? When we have 6 different rules, we want to write a relation of the form R is such that X maps onto Y. But there are 6 different possible Y's. So how do I do that? Well, I put a large bracket there and I have to list all the 6 equations for the regions where they apply. So the first equation there applies only between negative 5. You can see there between negative 5 and negative 3. The second equation there, second one, should apply between negative 3 and 0, and so on. Okay? So if I write that down, I've completed that. So if we write that down, what do we get? All right, writing that down, I should get that. It should make sense. It's telling me that the relation has a value of this for that range of values of x. When I move further, the value is 2, anywhere between negative 3 and 0, and the value is given by this rule between 0 and 2, given by that rule between 2 and 3, and so on. This is the relation notation for this particular relation. This gives us a chance to revise our coordinate geometry, gradient of a line, equation of a line, and so on, okay, while at the same time we tackle relation problems. Okay, let's go to the next part. Okay, here's another one. All right, I'm going to let you do this. Find the domain and the range in set-builder notation. Decide whether this is a discrete or continuous relation, and write down the relation notation. It's probably going to be difficult to write a relation notation for this, but you can still try and do it. Okay, the next one is a circle. Before we move on, I know that in the IB, for example, we do not study conics. which includes things like circles, ellipses, and so on. And because we don't do that, we probably don't know so much about the equation of a circle. But in general, the equation of a circle is given by x minus a squared plus x minus b squared equals r. Okay, this is the general equation of a circle. If a circle, before we go on, let's just see. I want to show some GeoGebra simulation to make you understand what A, B, and this R mean in the case of a circle, right? So very briefly, let me just show a simulation on this. Okay, so one moment. All right, so let's see, what can we do here? Do I have it? Here we go. Okay. Take a moment, but we should be able to see it clearly. So what I'm going to do, the A and B that I mentioned before, the A and the B are here. So I'm going to make B a 0. I'm also going to make A a 0. I'll also make A here a 0. Sorry. There we go. So you notice that this circle is at the center. Its origin is at the center. Its center is at the origin of the xy coordinate. All right. But r there is 16. Okay. What's the radius of the circle? If you check carefully, the radius is 4. Okay. So we are saying that when r, I think I can write here, when r, capital R there, this r here, is 16, the radius of the circle is 4. Okay, what about if I increase r? Let's increase r. I've increased to 17. I'm not so sure what that radius is. 18, I'm still not so sure. 19, I'm not sure. 20, I'm not sure. But if I move it to 25, the radius is 5. So when r is 25, the radius is 5. Okay, I can move backwards and see what happens if r is smaller. That was 16. What about 12? I'm not so sure about that. Looks like 3.5, but I'm not sure. 11, I am not sure. 10, I'm not sure. But 9, when capital R is 9, the radius is 3. So clearly you can see something is going on. Okay, when capital R is 6, I'm not sure. 5, I'm not so sure. Actually, I know what it is. But when it is 4, when capital R is 4, the radius appears to be 2. So in the equation R, x squared. So in the equation x minus a squared plus y minus b squared equals r, we know that this r is related to the radius of the circle. 9 is to 3, 16 is to 4, 25 is to 5, 4 is to 2. Clearly this r is the radius squared. So I can write this. I can just put here, instead of the capital R, I could replace with r squared, where r is the radius of the circle. Okay. What about A and B? You've probably already noticed what's going on, and if you've discussed transformation, then this also makes life a bit easy. I'll remove this now. Okay, so what happens if So notice here A and B are zeros, which is to say that this is equivalent to just saying x squared plus y squared is r squared. In this case, we have what? 2. So this is 2 squared, which is 4. This is the situation for this particular circle now. All right? Because A is 0 and B is 0. What happens if I move A, if I make A negative? Okay, so if I make A -1, look at what happens to the circle. All right? If I make A -1, the circle moves in this direction 1 step. Okay, similarly, if I make B -1, if I make B here -1, the circle moves up. Okay? Now if you look at the center of the circle, look at it carefully, you should notice it is at the point 1, 1. Okay, so the coordinates of the center of this circle has moved to 1, 1 when A and B are both -1. So we are saying that the equation with this, with x minus 1, right, or basically x plus, because A is -1, that makes this 1, right? So squared plus y plus 1 squared is r squared. Okay, effectively this is, actually this, what I did here, this is wrong. So what I have, this is what should be plus, this is what should be plus, plus like that. And so when we have minus here like that, it means the coordinates have moved to 1, 1. So that's the coordinate of the center, and the radius is 2. Okay, if I have x, say, plus 3 squared plus y minus 1 squared equals 9, then this is a circle of radius, first of all, whose center is -3, 1, and radius 3, like that. Okay, so this is how we determine the equation of a circle. So if eventually then, if I put a circle somewhere and you can tell the radius and the center of the circle, then you can use that information. If you have this detail, you can use the detail to determine the equation of the circle in the same way. Okay? All right, so I hope you got that. All right, conics is not part of the syllabus, but for those who want to write an IA, remember, an IA or an extended essay, please remember that you are allowed to roam anywhere, any part of mathematics that is relevant, that is at the same level as your course, right? So conics is at the same level as the course. It's just that it cannot fit in the 240 hours of the HL program, and so it's taken out as the least crucial at this juncture. So I will take these away now, and we are back there. So we have a circle whose center, coordinates of center we should be able to tell, and we should also be able to tell what the radius of this circle is. So given this circle, you're going to need the rule, basically the equation of the circle, to be able to write down a relation notation for it, okay? And so in order to write a relation notation, you must find the equation of the circle and then make y the subject of that circle, okay? So part A is for you to find the domain and range expressed in set builder notation. Part B is for you to decide whether this is a discrete or continuous relation, and part 3 is for you to determine the relation notation for this particular circular relation. Okay? So that's that. We move to the next part. Next part there. Okay, so here is the next one. So for this next one, again, now you have been given the relation equation for this. This is not supposed, well, this is supposed to be what here? There's supposed to be an x there. There is supposed to be an x here, right there. So this is x plus 3 squared and x minus 1, I think, squared. This is 1 over 10 is y. So please take note of this. It's supposed to be an x in there. So given that relation equation, okay, fix that please. Given that relation equation, write down, find the domain and the range. Decide whether this is a discrete or continuous relation, and then write down a relation notation for the relation. Notice this is completely filled circle at the end there, but there is an arrow here. When you see an arrow there, it means this continues on to infinity. So given that, if it is continuing on to infinity, what must be the domain? Okay, so where does the domain begin and where does it end, and what about the range? Okay, so write down the domain and the range, insert builder notation, decide whether this is discrete or continuous, and then write a relation notation for it. Okay, next one is kind of the same, and now it's truncated on both sides, except this is now the circle is not filled, or the dot is not filled. Okay, I want you to try that out. Here's another one that I want you to try out. Just answer this question for it. This is all part of question part 1, or question 1. Here is another one. A bit should be slightly challenging, but not really. If you are thinking on your feet, you should be able to complete these questions for this particular relation. Here's another one. This one is pretty straightforward. Just remember, these are not filled points, okay? And that arrow means this is continuing to infinity. Please fill that in. We will discuss the results later. And now this is question 2. In this question, draw a graph for the relation with the following domain and range. I'm giving you that information there, all right? State whether the relation is discrete or continuous. So that's pretty straightforward. Excuse me. Question 2 continues again. So this for the same instructions. There are the pieces of information given. They should be familiar already for those who have done quadratic function. That would be the vertex form. So you can sketch that graph there easily. Try that out. This particular relation is given in the form of a mapping diagram. Again, represent that on a grid like that, and respond to those questions. The second last question is given there. A 20-gallon bathtub is draining at a rate of 2.50 gallons per minute. The number of gallons, G, remaining relates to the number of minutes, M. Okay, so G and M are like X and Y. All right, write down the equation for the relation. Okay, 2.5 gallons per minute. Okay, graph the relation and then state whether this, whether the domain is real, not real, but this is supposed to be discrete or continuous. Okay, it is real, but is it discrete or is it continuous? So this here is supposed to be this. Cancel that and put here discrete. So decide whether it is discrete or it is continuous. Okay, and the last question there, is, oh, by the way, just in case you didn't know, you don't need it, but if you didn't know, 1 gallon is approximately 4.55 liters. It's 4.546, I think, to 4 significant figures. All right, so that's that there. Try that out. And lastly, the data shown in the table, discrete or continuous? Explain your answer. So there is a table of data. Do you think this is discrete or is it continuous? You would need to have watched video 1 and video 2 to be able to answer this question appropriately. All right, so hopefully you try these questions out and let me know if you have any difficulties. If you want us to go through any of them, we can do so without any problem. Please like the video if you did like it, and also so that when lesson 4 comes through, you can get notification, right? Thank you very much. See you for the next one.